Hello everyone, welcome back to CpE2301. We are now in lecture 2 in Unit 4. So in this lecture, we'll be tackling about the flip-flops and its characteristic tables and also its state equations. So what is a flip-flop? A flip-flop is a binary storage device that is capable of storing one bit information and has a timing characteristics. So again, this is a binary storage device, and then it is storing one bit of information per flip-flop and has a timing characteristics. So imagine in the computers we have their RAMs, and then in the RAM there are how many memory we can store, and then those memory elements are what we call flip-flop. So for example, if there are 4 gigabytes of memory, so there's around 4 gigabytes times 8 of flip-flops. So the difference between latches and flip-flops here is that latches, based on the um, previous lecture, that they are level sensitive, and then flip-flops are the edge sensitive. So what this means is that when we create the timing characteristics where the transition between 0 to 1 or 1 to 0, so we determine what are its differences. So when the data is around 1 and around 0, that's your level sensitive. For the edge sensitive is the transition between 0 to 1 and 1 to 0. So the term we use there is the active edge. So later on in the circuits and the flip-flops, the datasheet will refer you to what kind of active edge it is. So we have here 2 kinds. So it refers to the clock edge, refers to it's either a rising or positive edge, and then on the other hand it is a falling or negative edge. Rising edge is from 0 to 1 or low to high voltage, whereas for the negative or falling edge, that's from high to low or 1 to 0. There are 4 types of flip-flops. So we have here the D flip-flop, the T flip-flop, SR flip-flop, and JK flip-flop. So first we have here D flip-flop. So D flip-flop is created with the use of 2 D latches. Okay, so for these latches, so we have here enable. So enable is being controlled by a clock. So remember that in the description here that a flip-flop is a timing characteristic, so we use a clock. So a clock is a pulse that depends on the frequency we store or use for the clock. So let's say if the clock is running in 1 second per pulse, so it has a 1 second from low to high, and then another second to high to low. And at the same time, it differs from a duty cycle being used. Okay, so below here is the characteristics of your D flip-flop. So when a clock is 0 or 1, whatever the value of the D input here, and then the current state of the queue, the output here is the Q next is 0 or 1 or whatever the value of your Q is. So by the way, since we are dealing with timing characteristics, we need to identify or reminded that we have here the Q present and Q next. Q present is the current value of your Q, whereas for the Q next, that is what would be the next value depending on the input scenario. And then Q next bar is just the complement of Q next. So here, if we have here that if it is a rising edge, and then the value of your D flip-flop is 0, whatever the current value of your Q next will be 0. And then if the if the clock is rising edge, for this case this is rising edge because of the arrow, but later on the datasheet will also refer you if there is a falling edge. For this case, in this image right here in the right side, this is a rising edge. The difference between rising and falling edge is that it has a bubble here. So if the value of your D is 1, then whatever the value of your Q here is, the value of your Q next is 1. So as you can see, whatever the value of your D here, the output of your Q here is the same. So since we are dealing with status, so we refer 0 here as reset, and then 1 here as set. So again, I'll be reminding you that this is Q present and then Q next. Q present is here, and then Q next will be here. Basically, this is again the inside of your D flip-flop. So aside from that one, you can also create a D flip-flop using a NAND gates here. So this is the equivalent NAND gate of your D flip-flop using the SR latch. This is a positive edge triggered flip-flop. So the clock is triggering these NAND gates, and then the input is in this side. So can simulate this one to refer in this characteristic table. So basically either this version or that version, it would be the same. So let us compare this one in your comparison here. So you have here gated D latch for this Q. Basically this is your D latch, and then the other two here are your D flip-flop. So one is positive, one is negative because it has the bubble in the clock side. So this is, we want to compare the outputs of these three, given that they have the same inputs of your clock and the inputs. So this is the clock. Basically this is your timing diagram. So later on in our sit work, quizzes and exams, we want you to generate this timing diagram. So this is clock, high, low, and then this is the horizontal axis is in terms of time. So this is time at 0 at time at infinity here. And then this is the, let's say, a setup scenario of your D input. So what will be your output for in this case? So in the D latch here, so this is high and then low, your output is also low, and then this is high and then another high. For in this case, the clock here is low, and then since this is active enabled or active high enabled, so it will only be enabled when it is a high signal. So in this case, in this part, the output will still be low, and then the time of the clock here is high, and then it has the value of your D changes, so it also change the output of your D latch. And then this is now low, and then that is now disabled. So even though this part here goes low, so it is steady because it is this was disabled. So whatever value of your D here doesn't affect your output because it is disabled from this part. So how about our flip-flop? So in the flip-flop, it is an edge sensitive. So in this case, we have here a positive edge. So what we want is to look for a positive edge part of your clock cycle. So since that is positive edge, we don't look for the high to low, but we want to look for low to high. So initially, let's say QB is in high state, and then at such time it reads that the clock is low to high, so it changes whatever the status of your D, since the status around this time is 0, so it changes the value of your Q from 1 to 0, or whatever the value is, to 0. So that's why it moves down here. Whereas in the negative edge here, in the third flip-flop here, so it is now the other way around. We want to look here from high to low instead of low to high. So again, QC here is initially high until such time it searches for a high to low clock input, and then whatever the value of your D input here, so since the D input here is low, so it changes from high to low, and then it until such time it looks for another negative edge, high to low. So the next one is in here, since the value of your D at that time, or this time here, is 1, so it changes from 0 to 1. So again, we look at the edge first, and then what will be the current value of the D input at that point. So whatever the current or the present value of your Q, changing that one to 0 if the D value is 0, and then changing it to 1 if the D value is 1. So this is another application of your D flip-flop. So this is a D flip-flop with enable. So we have another input here, enable. So if the enable here is 0 or being disabled, so the D flip-flop won't respond to your whatever the D input is. So whatever the current value of your Q will remain as is. Then when if you enable this one, becomes 1, so that's the time the D flip-flop will activate. Okay. Again, we have here the Q present is included in your input side, and then a Q next is for your output side. So even though what you see here is that Q is in the output, so since we are again dealing with the timing constraints and characteristic, so there are two status of your output. So the current state of your output and then the next state of your output. So if you want to be more comfortable, you can also place here the Q present, and then this is Q next. So aside from the D flip-flop with enable, so we have here the asynchronous inputs. So what it means by asynchronous, it doesn't look for a timing or a clock for it to be proceeded or to be activated. So okay, D flip-flop is asynchronous. Again, we are now in a synchronous or sequential circuits. So these are synchronous. The outputs of your D flip-flop are synchronous to the clock, depending on a characteristic of your flip-flop. So either positive edge or negative edge clock cycle. But for the asynchronous inputs, these are additional inputs to your IC here. It overrides the output of your flip-flop without the regards of the clock. So either the clock is present or not, high or low, whatever being set for the asynchronous inputs here, it will generate the value of your Q. So we have here two asynchronous inputs. So we have here the preset and clear. So when the preset is triggered, so the output of your Q will be 1. When the clear input is being triggered, the output of your Q is now 0. So on the left side here is the example of the D-latch with enable with a preset and clear asynchronous inputs, and then on the right side here is the D flip-flop with enable and with the preset and clear. Okay, and the next one here is your SR flip-flop. So in the SR flip-flop here, so this is another example, a type of SR, which is a negative edge triggered SR flip-flop, and then again there are also a positive edge equivalent. But for the example here in the discussion, it would be a negative edge. So this is the circuit of your negative edge triggered SR flip-flop from your SR latch. So this is now the summary of the truth table of the SR flip-flop. So for this case, we are looking for the negative edge. So when the clock here is on the from high to low, whatever the value of your SR here, for example, if the value of your SR is 0, 0, what would be the change or status of your queue to queue next, queue present to queue next. So if the SR is 0, 0, in this case, whatever the value of your queue is, the output of your queue next is just the same. So in this case, what we call here is to hold the current value or copy the current value. So whatever the value of your queue present is, queue next value again is the same. If the SR value at a certain edge here of your clock is 0, 1, the queue value either 0 or 1, it resets the value to 0. And then if the value of your SR is 1, 0, and then whatever the value of your queue here, the value of your queue next output here is 1 or set. So that's why the term here SR or set reset flip-flop. So we have here three characteristics: hold, reset, and set. How about if the SR becomes 1, 1? What will happen to the queue here? So for in this case, based on the data sheets and characteristic for this one, it is being undefined. So basically we do not include this part of the SR flip-flop. So it may happen in a certain time if the value is 1, 1, but we discourage to apply this one in your circuit. But later on you would know why or the updates for this flip-flop. So this is another flip-flop circuit. So this is a T flip-flop. It is being derived using your D flip-flop. So what it do here is that based on the characteristic table here, so again this is based on a clock edge, so either a positive or negative edge. Let's say first here, if the value of your T here is 0, so what will happen to the value of your Q to the next state? So from 0 to 0, 1 to 1. So in this case, this is a hold state or copy state. So how about if the value of your T is 1? So whatever the value of your Q here, so 0 or 1, so if the T is 1, it inverts the value of your Q. So from 0 to 1, 1 to 0. So this is what we mean by inverting or toggle. So that's why the name of your flip-flop is T, because it toggles the status of your flip-flop. So again, the characteristic for T flip-flop here is hold if the T value is 0, and then it would toggle if the T value is 1. Okay. So for the last flip-flop here is your JK flip-flop. So JK flip-flop is also derived from your D flip-flop here. So based on your characteristic table here, we have here if the value of your JK is 0, 0 here, And then if your Q present here is either 0 or 1, the next status for your Q will still become 0 and 1. So again, in this part, this is your hold state. And then if the value of your JK is 0, 1, so what will happen to your current or present Q? So it resets the value to 0. And then 1, 0 for JK, it sets the value to 1 from present to next. So 0 to 1, 1 to 1. And then last will be what will happen to the present value of your Q if the JK value is 1, 1. So from 0 to 1 and 1 to 0. So this is your toggle or inverting status. So when you observe in this manner, so we have here hold, reset, set, toggle, we would acknowledge that JK here, or the JK flip-flop here, is an universal flip-flop. So what it means is that you can create the flip-flop equivalent for a JK flip-flop, an SR equivalent flip-flop to your JK flip-flop, and a T equivalent flip-flop using a JK flip-flop. So all of those discussions will be discussed on the next lecture. But for now, I am discussing you what are the characteristics of your flip-flops. So in summary, this is your flip-flop characteristic tables. We all know that all of the flip-flops are clock sensitive or edge sensitive in this case. So what we'll be knowing here is that, let's say for a JK, if this is 0, 0, the output of your Q, this is T plus 1 or time plus 1, which is the next time cycle. So the output of that one is the QT, or the Q present, or the current time. So that state will be no change or hold. JK value 0, 1, the output of your Q next here is 0, so the status is reset. 1 for 1, 0, set 1, 1. This is Q bar T, so it is a complement of your present Q. And SR, so you have here no change, reset, set, and then undefined. And then D flip-flop, reset and set. T flip-flop here is no change and complement. So how would you generate a characteristic equations from the flip-flops? So for an example here, JK flip-flop, and we want to create the equation for that flip-flop. So we'll base that one in this truth table. So again, our output here is the Q next here. Since we have here 3 inputs, so J, K, and Q. So this is just the same. We will get the min terms and then get the SOP form for that one. So this is 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. And then apply your simplification method here. So using the theorems and postulates here, so this is equivalent to 1. So you have here k bar q or jq bar. So that is now the equation for your q next. And then the rest would be for your own. So alternatively, we can also draw state diagrams here. So what is a state diagram? So a state diagram here in binary logic uses only two shapes, the circle and also the unidirectional arrow. So the circle contains the output status, while the unidirectional arrow here contains the input conditions. So just to clarify, the unidirectional arrow only uses one arrowhead. So this illustrates the transition from the present state to the next state. So therefore, it cannot be bidirectional. So let's take an example here. So this is an example of a door lock system state diagram. So let's say the problem here is that the door lock system uses a push button to lock or unlock the door. So in this case, we have here push button for your inputs, and then the door or the locking system for the door is the output. So the door is initially locked and only opens when the button is pushed. So that's the characteristic of your door lock system. So when the pushed button gives, or rather the pushed button, it gives the logic high or button is equals to 1 to the system and unlocks the door, which is lock equals 0. Otherwise, when the button is not pushed, so button is 0, the door is locked, so lock is equals to 1. So again, we have here two devices, the input device push button. So I named the variable for that push button, and then the output here is the lock of the door. So either the lock is 0 or lock is 1. So since in the state diagram here, we first draw the circle. So what are the output states of your diagram? So in that case, lock 0 and lock 1 is your circle states. So this is one state and then another state. The door is not locked, the door is locked. And then the next step here is to get the transition from every state. So based on the definition above here is that when the door is not locked, and then the input here is being, let's say if you do not push the button is equals to 0 in this state. So what will happen? Again, the scenario here is that lock is 0, it is open. So if you do not push the button, it will lock the door. So from this state to the next state here, so we draw an arrow and then place there when the button is 0. On the other hand, if the lock is locked or lock equals to 1, and then when we push the button, our button equals to 1, so it changes the state from 1 to 0. So this is now what it looks like. Can we say that is this complete? No. Even though that this is now based on the definition here, it still lacks a definition of the system. So what will happen if during this time lock at 0, if the button is still being pushed? What will happen? Does it still lock the door or remain as is? So when in this state, if the input is still 1, so it goes back to itself that the door is still unlocked. And then on the other side here is that when the button is still 0 or not pushed, so it will always lock the door. So without this scenario, that the button condition here, if the value is 0, so it might have some tendencies to create a scenarios that makes the door unviable. So to complete that one, so we have this arrow here. So again, lock 1 here is being locked, so the door is locked. I am not pushing the button, so it still locks the door. And then I push the button, so it unlocks. So I'm still pushing the button, so it still unlocks. And then I release the button, so it locks again the door. Okay. So that's how you create the state diagram. So how do we apply this one into your flip-flops? So this is an example of the SR flip-flop state diagram. So we have here your truth table. So there are only two scenarios of your output, when the Q is equals to 0 or Q equals to 1. So let's start with Q equals to 0. So this is the present state, Q equals to 0. So there are three inputs in this case, if either 0, 0, 0, 1, or 1, 0. So if we input here 0, 0, so the status is no change, so it only goes back to itself. But if we use 0, 1, that is a reset state, so again it goes back to itself. So the time it only changes is that if the value of your SR is 1, 0, so that is a set state, so now the current value of your Q here, or the present Q, is now transitioned to the next state, which is Q equals to 1. And then on this state, this is now your current state. If the current input in this state here is 0, 0 or 1, 0, so that is no change for 0, 0, so it doesn't change. 1, 0, it is a set, or 1, so the value of your Q next is the same as your Q present. It only changes when the SR value is 0, 1, or reset state if the present is Q1, and then changes that one to Q0 for the next state. So that's how you create your state diagrams. So that ends my lecture. Thank you for listening. If you have any more questions and clarifications, please contact us, and we love your feedback on this one.